Okay, so let's take a look at this equation again. We've got this equation PbNO3 which is aqueous, plus 2 moles of Ki, which is also aqueous, gives us PbI2, which we now know is a solid because of the solubility rules, and 2 moles of KNO3 aqueous. Now this equation, not only is it a double displacement equation, but the way that this entire equation is written out, this is an example of a molecular equation. Now, in a molecular equation, what we're doing is that we write the formulas of the compounds as if they don't break apart. As if they don't break apart or dissociate. Okay, now molecular equations are awesome because it tells us exactly what compounds to use, but it doesn't describe what's going on at the atomic level. So molecular equations are great because it tells us what compounds we're going to use. But it does not tell us what occurs at the atomic level. It does not describe what occurs at the atomic level. Okay, now sure, it tells us what compounds are formed, but are all of the ions participating? No, and that's the main problem here. We know exactly what compounds we're going to use. We know exactly what compounds are going to form, but this is not telling us what each of the ions are doing, how the ions are participating. Are there ions driving this chemical equation? And there are. So we need to get that information out. How do we get that information out of this? And so that's the next step. So we can actually rewrite that equation to show all the ions that are present in that chemical reaction. And when we write that equation out, we call this the full ionic equation, where we rewrite the molecular equation to show what is actually dissociating, what is actually dissociating. So the full ionic equation, we rewrite the molecular equation to show what dissociates. Okay, so here's our equation. PbNO3 plus 2 moles of Ki yields PbI2 plus 2 moles of KNO3. This is our molecular equation. So everything dissociates because it's ionic. The only thing that does not is our solid, is our precipitate, because that comes out of solution. So to rewrite this as a full ionic equation is that we write everything as ions except for our precipitate, the PbI2. So that means we would have Pb2 plus aqueous plus 2 moles of NO3 minus aqueous plus 2 moles of K plus aqueous plus 2 moles of I minus aqueous, and that all yields PbI2, which is a solid, plus 2 moles of K plus aqueous plus 2 moles of NO3 minus aqueous. And so there it is. This is your full ionic equation. Okay. Now again, why was PbI2 singled out? Why are we writing that together as a molecule instead of as ions, because remember, that's our precipitate. That comes out of solution. All right. Now, if you notice something about this full ionic equation, there's ions that show up on the left-hand side and the right-hand side. So let me highlight those for you. Like, for instance, potassium ion shows up on the left and the right-hand sides of the equation. Nitrate ion shows up on the left and the right-hand sides of the equation. Now, when we have ions that show up on both sides of the chemical equation and they're not really being used to form a product, we give a special name to those. We call these spectator ions. Spectator ions. These are ions that are not involved in the reaction. Okay, so in that case, potassium ion and nitrate ion, these are spectator ions for this particular reaction. Now, when we cancel out those spectator ions, so if we were to cancel out those spectator ions, what we're left with is something called the net ionic equation, which only shows us that what species are actually taking part of that reaction. So I'll tell you what, let's rewrite this so that way we got it all straight. So the molecular equation went like this: PbNO3 2 aqueous plus 2 moles of Ki aqueous yields PbI2, and that's a solid, plus 2 moles of KNO3, and that was aqueous. All right, so that was your molecular equation. The net ionic equation, we write everything as ions except for the precipitate. So you got Pb2 plus 2 moles of NO3 minus, aqueous, plus 2 moles of K plus, aqueous, plus 2 moles of I minus, aqueous, yields PbI2, solid, plus 2 moles of K plus, aqueous, plus 2 moles of NO3 minus, aqueous. Now, what I'm going to do is highlight the spectator ions. So here's our K plus. Here's our nitrate ion. Now, if I ignore the spectator ions, okay, and I take them out, what we're left with is the net ionic equation, which is this: Pb2 plus aqueous plus 2I minus aqueous yields PbI2 solid. And so this reaction right here is what is actually driving this entire process. And that's it. So when we have a precipitation reaction, we can get to the heart of the matter and try to figure out what's going on at the atomic level by rewriting a molecular equation to get us the full ionic equation, drop the spectator ions, determine what the spectator ions, and then rewrite the equation as a net ionic equation. So in order to get to the net ionic equation, you have to write the full ionic equation. The only way you can get a full ionic equation is to write the molecular equation. All right, so let's try a problem out. So predict the precipitate produced by mixing an AlNO3 solution with an NaOH solution, and then write the net ionic equation for this reaction. All right, so the way we're going to do this, we have to predict the products of this reaction. So here we go. So we've got AlNO3 3, and we're told that this is aqueous. Okay, and this is going to react with sodium hydroxide. All right. Now, this is a double displacement reaction. So since it's a double displacement reaction, what we're going to do is replace the cations. The cation switch. All right, so predicting the products of the reaction, we should get Al OH and NaNO3. All right, now we got to balance the charges. So for Al, that's going to be 3 plus, NO3 is minus 1, Na is plus 1, OH is minus 1. All right, so that means Al should be plus 3, OH is minus 1, Na is plus 1, NO3 minus 1. So that means that I should put parentheses around the OH and then subscript 3 for that. All right. So before we do anything else, let's also make sure that this is balanced. Okay, so you've got 1 aluminum on the left, you've got 1 aluminum on the right, you got 3 nitrate ions on the left, you've got 1 on the right, so this has to be a 3 in front of the sodium. So you've got 3 sodiums over here on the right. You've got 1 on the left, so you have to put a 3 in front of that. So that way you get 3 hydroxides, and we're balanced. All right, so now we got a balanced chemical equation. Now before we do anything else, we got to predict what are the phases of our products. So are these precipitates or are they aqueous? All right, to do that, we got to go back to the solubility rules. So let's do that. So our 2 products was AlOH3, and we had NaNO3. Okay, so let's see what we got. So let's deal with the NaNO3. So sodium is in family 1A, and that tells us that sodium is going to be soluble, and there's no exceptions to that. Now, we can double check this because we got the nitrate ion. The nitrate also tells us that this is going to be soluble, so automatically we know that NaNO3 is going to be aqueous. All right. So we could assume that AlOH3 is also going to be our precipitate, but let's verify that. So insoluble compounds, the rules there, hydroxide ions are insoluble except for hydroxides of group 1 cations, NH4+, Ca2+, strontium2+, and barium2+. So aluminum is family 3A, so that doesn't fall here. So this has to be insoluble. So we know what the phases of our products are. All right, so let's go back to our problem. Now we know AlOH3, that's a solid, and NaNO3, that's aqueous. All right, so this is our molecular equation. We're good now. So next step is that we've got to rewrite this equation and assume that everything is in ions, everything dissociates except for your precipitate. So we need to write the full ionic equation. So we're going to write everything as ions. So to get the full ionic equation, I would start writing our ions. So we have Al3 plus, aqueous plus 3 nitrate ions, okay, plus 3 sodium ions, plus 3 hydroxide ions, yields AlOH3, which is our solid, plus 3 sodium ions, plus 3 nitrate ions. All right. Now, the next step is that we've got to figure out what cancels out on the left and the right-hand side, what shows up. So sodium ion for sure, that shows up on the left and the right. And the nitrate ion also shows up on the left and the right. So once we cancel out what we're left with, okay, we can write our net ionic equation, Al3 plus, aqueous, plus 3 hydroxide ions, aqueous, yields AlOH3. And that's our solid. And there it is. So that's how we went from a molecular equation to a full ionic equation to a net ionic equation.